SwayamPrabha. Digital India. Educated India.
Yes, good morning. Today we'll be trying to write equations of motion for an aircraft which will be assumed to be moving in a vertical plane. That is, it will be going like this. It is not doing any side motion. Okay? So we are thinking and trying to model through equation of motion that as if the aircraft is on a climb like this, maintaining the vertical plane. Okay? And that is typically represented here. Before we try to write the equations of motion, let us understand few nomenclature. This dotted line, what you are seeing, this is basically the chord line. That is, I have joined the leading edge and trailing edge of the wing by a straight line and extended it. It has a significance because wing is the primary lifting component, right? So what is the angle between the wing chord line and the free stream velocity? That gives you the angle of attack in a vertical plane, right? And that is primarily responsible for the lift, because wing is primarily required to generate lift. So this is the chord line, and every aircraft will have an engine, because after all it has to have enough thrust to overcome the drag experienced by the airplane. So let's say engine is installed in such a way the thrust vector is in this direction, which is not exactly on the velocity direction, because this airplane will have not only thrust as a force, it also will have a gravity, it will have a drag. So resultant velocity will be somewhere different than the thrust direction. And let's say the angle between thrust and velocity vector in the vertical plane is alpha t, t for thrust. And this line is the horizontal line, and gamma by is called flight path angle. Gamma is flight path angle. What is the meaning of flight path angle? If the airplane is going up or climbing like this, then I can trace the center of gravity of the airplane by following the velocity vector, right? Like this. So this velocity vector, how much angle it makes with the horizontal is the flight path angle. And now if I see here, if this is the velocity direction, by definition the drag will be exactly opposing the velocity, and that is why drawn like this. The drag lift will be perpendicular to velocity, so lift is perpendicular to this velocity vector, and weight will be acting vertically down, so weight is here. Now I will write equation of motion along velocity direction, along the v direction, and one perpendicular to v direction. So what happens if I write along velocity direction? I could see the thrust cos alpha t is component here, which will try to accelerate this machine, whereas the drag will try to decelerate. So t cos alpha t minus d. Same time, the weight also will have a component along velocity direction, which will also try to oppose it. So there is a w sine gamma, and this net force will give an acceleration which is m dv by dt. But please note a word of caution here. We are assuming m is constant. That means we are actually assuming that the weight change because of fuel consumption is negligible. Right? Now we'll be writing equation perpendicular to v, and you could see forces acting on this vehicle perpendicular to v. One of them is lift, another is component of thrust, another is component of weight. So if I want to write this equation now, this lift perpendicular to v, t is the component of thrust, and then I have to add w cos gamma, and this net force will generate an acceleration, centripetal type acceleration, and which I am equating as mv square by r. Right? Once you are writing this second equation, it will help you in reminding this thrust, which is responsible for changing the velocity vector, and that is why we have centripetal acceleration. Similarly here also, this force, net force L plus T sin alpha t minus W cos gamma will try to change the velocity vector, direction of velocity, and in turn it will generate centripetal acceleration. So these are the two equations we will be using to derive something which are of very, very importance. We will be primarily dealing with static performance, what do you mean by static performance? We are actually concentrating on performance which are non-accelerated, that is unaccelerated flight. Okay? That is, if I am cruising at constant velocity. If I am climbing at constant velocity. So we are not doing any flight where there is acceleration. So if I now come back to these two equations, the first equation for static performance becomes T cos alpha t minus D minus W sin gamma equal to 0, and second one becomes L plus T sin alpha t minus W cos gamma equal to 0. Now see, if we impose some approximation, which are fairly good approximation, for example alpha t will be very, very small, right? So for all simplification, I can assume that alpha t is small such that cos alpha t is 1 and sin alpha t goes to 0. Okay? Goes to alpha t, and alpha t is small, it goes to 0. Right? If I now put these conditions here, what do I get? Then I get, if I put cos alpha t tends to 1 and alpha t for tends to 0, sin alpha t tends to 0. Tends to 0 because it tends to alpha t and alpha t tends to 0. This you have to be very careful, because when you are making assumption alpha t small, sin alpha t going to 0 or very small, but same time we should be careful that this term is t sin alpha t. If the t is very large, sometimes it may not be very, very small to be neglected, but we are assuming that good enough small so that I can neglect this term. 1 I write t cos alpha t minus D minus W sin gamma equal to 0. If alpha t 0, cos alpha t tends to 1. This gives me T minus D minus W sin gamma equal to 0. And the second equation, I get L minus W cos gamma equal to 0. This is second equation. Now see here, if I am talking about traditional cruise, that is, I am cruising like this with gamma 0. Because if gamma is non-zero, if gamma is positive, I am climbing. If gamma is negative, I am descending. So we are talking about a cruise where I cannot reduce the altitude. So I am going for a gamma equal to 0. So if gamma equal to 0, which is true for cruise, then I have T equal to D and lift equal to weight. So now you understand, when I draw a diagram like this, what are the approximation has gone into it? One is, if I repeat, alpha t is small, that is angle between thrust and the velocity vector is very small, and also gamma equal to 0, right? Then only I can directly draw this. This diagram should not confuse you in thinking that alpha is 0, because if alpha is 0, where from do I get lift, right? Whole game, whole episode of airplane performance is towards generating requisite alpha or requisite CL. You will understand soon, right? So this is a very important relation, and we will be using it rigorously. Okay, now it's very simple to write on the blackboard that thrust equal to drag and lift equal to weight. But first question comes, who will give this thrust? I need an engine. What type of engine? So this part is taken care by engine. And the drag, what should be our aim? Mostly, especially for cruise, we should try to fly such a condition that the drag is minimum. So this is more governed by the aerodynamic design. Aerodynamic design, airframe design. They actually attribute to drag in a sense that if I make an efficient airframe, I can have drag low. If I am making a airframe which is blunt, I'll have more drag for a given speed, right? Now, but the question will come, okay, it is fine. For thrust, I need engine. For drag, I need aerodynamic design so that the total resistance is less. For lift also will be decided by aerodynamic design. And more importantly, lift means wing, who is primarily responsible. So we'll design a wing area so that we get sufficient lift for a given velocity and given altitude. And weight. Why weight is important? See, in cruise, if I'm cruising, my aim is I must fly at a speed such that the lift is good enough to balance the weight. So if we are going on increasing the weight, then to generate that lift to balance the weight also will be demanding, and we may not be able to fly at that speed to really balance the weight. So we have to be very careful when we are deciding on the weight, even at cruise conditions. Okay, now let us first try to understand what is the thrust required. We are talking about cruise flight, let us say. As I told you, these are very important equations, thrust equal to drag and lift equal to weight. So I can club them. I can write thrust equal to W by L by D. I can write that W by CL by CD. This is an expression to get thrust required for cruise. But how to calculate this? Question is this. How do I calculate? Let us go one step more to understand how do I calculate. Say TR, we now represent thrust required. That is for a given W, this is given by CL by CD. And by now you know CD I can write as CD naught plus K CL square, which is the drag polar of the airplane. How do I get CL? CL is, who will give us the CL? Why do we need a CL? I need a CL to balance the weight, right? So where from I get the value of CL? How much CL is required? That is from lift equal to W. So I know half rho V square S CL equal to W. So I know CL equal to 2W by rho V square. So now again see this, what is our aim? Our aim is to calculate thrust required, right? So I know what is the weight of the airplane. I know what is the CL I should be flying, because I know what is the speed I will be flying. I know what is the altitude I will be flying. I know the value of CD naught, because this is constant for a given airplane. And also K, you know, K is 1 by pi aspect ratio E, where E is the Oswald efficiency. It could be between 0.7 to 0.9. So all these values are known. Once I know this, for a given flight condition, I know CD, I know CL, so I can find out CL by CD, as simple as that. Okay? So what is that? I know CD, I know CL, so I can find out CL by CD. It is as straightforward, and I can use this expression W by CL by CD is thrust required. But the story doesn't end here. We have to give a more insight into this expression so that a designer can handle this situation. Let us ask ourselves, why do I need thrust required? What is our aim? Our aim is we are requiring thrust required just to balance the drag. And who is giving us drag? Drag is because of zero lift drag, CD naught, and because we are requiring lift, that is also giving a drag, which I call induced drag, right? So let us see, if I write now thrust equal to drag, I'm equal to half rho V square S CD, and then further I write as half rho V square S CD naught plus KCL square. One thing I know, if I want to find out what is the thrust required for different speed, meaning thereby at different speed drag also will increase. So to balance that drag, I need to increase the thrust, right? So I want to know the variation of thrust required versus speed through drag. This is important. Through drag, I am trying to make an assessment. One thing physically, I know that this gentleman CD naught is going to be constant for low speeds, right? But as I am increasing the speed, my CL requirement will go on reducing for same height, maintaining the same height. That is, if I am flying here at this altitude, say rho, and I am flying at a V1, so I need a CL1, which is given by CL1 equal to 2W by S by rho V1 square. Now suppose I want to fly at same altitude again, but I want to fly at V2. Then I required CL2, right? So CL2 will be what? CL2 will be 2W by S rho V2 square. So which one will be more? CL1 will be more or CL2 will be more? If V2 is less than V1, that is, initially, let's say I'm going at 80 meter per second, at the height 10 kilometer, I need a CL. Now, same height, I am flying at 70 meter per second, then CL requirement will be more because I want to balance the weight. So if V2 is less than V1, that implies CL2 is greater than CL1. To maintain cruise at same altitude. CL2 greater than CL1 means the induced drag at CL2 at V2 will be more. So KCL2 square will be greater than KCL1 square. So what is the message? Message is, if I am maintaining the cruise at same altitude, if I am flying at a higher speed, then the induced drag will be less. As the speed increases, the induced drag component will reduce because CL requirement is less. If I am flying at a lower speed, then CL requirement will increase, so the induced drag part will increase. Okay, so now if I understand this and try to figure out how thrust required will change with V. One is, by this understanding, I can get a feel of the variation, but if I want to write explicit expression, then I will do one more step. Thrust is half rho V square S CD naught plus half rho V square S K into CL square, but we know CL is 2W by rho V square S. So I plug this here. So what do I get? I get thrust required equal to half rho V square S CD naught plus 2W square by rho V square S. This is clear? How will you get this? I am substituting CL here by this expression. So CL square will be 4W square rho square V to the power 4S square, and this they will get cancelled from here. So we will get 2W square rho V square S. Now you could see explicitly, as I am increasing the speed, this thrust required, which is basically the drag, goes on increasing with V. However, the second term, as V is increased, this term goes down, which is by physics you understand, as I am increasing the speed, this term, which is basically induced drag, will go on reducing. So it is consistent with whatever physical understanding we have, and we always will refer the first term as zero lift drag or thrust, and second one is induced drag. Induced means who has induced this drag? This is lift induced drag, because it is coming from CL, and by physics also you know this comes because if there is a lift, there is a pressure difference between the lower portion and the upper portion of the wing, and there will be vortices forming at the wing tips, and that will take out energy because this will have rotational energy, so naturally there will be a loss of speed. Okay, and we attribute that in terms of induced drag. So now if I see this, I could see that the zero lift drag, if I want to plot, it will be going like this. It will go on increasing with V. However, the second term will go on reducing as V increases, and if I find the net will be something like this, and this is the portion which will be giving a name V for thrust required minimum. Right? See, by drawing this, I have almost given a message that the V for thrust required minimum will be somewhere at the point where the parasite and the induced drag, they intersect. Whether they will intersect here or not, let us analytically see this. How do I interpret this point? I am trying to interpret this point, which is almost tangent here. This is the thrust required minimum, right? So this is the velocity for thrust required minimum. And I'll do some steps, algebraic steps, using this equation only to find out what is the condition at which the V will be this V and the thrust required will be thrust required minimum, right? Let us first understand thrust required, we have seen is W by CL by CD. One thing is very clear to us, if I want to have thrust required minimum, this implies for a given weight, CL by CD should be maximum, right? For a given W, CL by CD should be maximum. What is the meaning of CL by CD to be maximum? Question is this. You know that, we know that CD is basically CD naught plus KCL square. So what is CL by CD? Will be CL by CD naught plus KCL square. So what is the question we are going to ask? We are going to ask question, what is that CL I should fly so that CL by CD is maximum? This clear? The question is, what is that CL I should fly so that CL by CD is maximum? When I say what is that CL I should fly, and for a cruise, it is equivalent saying what is the speed I should fly for which CL by CD is maximum, because speed and CL are related. Okay, now how do I check for maximizing the CL by CD? The rule is very simple. You differentiate. Then what do you get? You get CD naught plus KCL square into 1 minus CL into 2K into CL divided by CD naught plus KCL square whole square. And to see it is turning point or not, I equate this equal to 0. So I find CD naught plus KCL square minus 2K CL square equal to 0. So I get a condition KCL square equal to CD naught. You could see if I take the second derivative, just check whether this turning point is a maxima or not. Only you need to see that second derivative should be negative, which is straightforward from here. If I take a second derivative of it, I will again get a negative value less than 0. So it is indeed a maxima. But let's come back to the physics of the situation. What is KCL square? It was the induced drag. What was CD naught? The parasite drag. So what is the message? It says it is that CL at which induced drag is equal to parasite drag or zero lift drag. That is the CL at which the thrust required is minimum. Now you will come back to this diagram. If you recall, we had induced drag going like this, parasite drag going like this. This is the point where CDI is equal to CD naught. So the net, when I am drawing, I know that this is indeed the V for thrust required minimum. That is, it is that V at which KCL square equal to CD naught, or I answer my question that to get thrust required minimum, I must fly at CL, which is given by CD naught by K under root. Is it clear? Okay, it is fine for us. It is clear that CL is CD naught by K. However, for a pilot, if you tell, dear sir, please fly at CL equal to CD naught by K, he may not understand. He is not an aerodynamist. Right? So how do I communicate to the pilot? That is also an important question. Now let us see. When I say CL equal to CD naught by K, what is the speed I should fly so that thrust required is minimum? V will be under root 2 W by S, rho S is, sorry, S is not here, so CL, that is CD naught by K. Right? For a given airplane, any airplane which will be flying, you will be knowing CD equal to CD naught plus K CL square. This drag polar will be known to you. You know the value of K, you know the value of CD naught, you know the weight, you know the wing area, and what altitude you are flying, density also you know. So you actually know to fly at that altitude for thrust required minimum, I must fly at this speed V. Okay? So this will tell you what is the V pilot will need to fly. Do not forget, it cannot be any arbitrary altitude because we have to satisfy that it is following a cruise condition. So you have to also ensure that lift equal to weight, that is half rho V square S CL equal to W, or this, if I further write, I will find that half rho V square S CL is nothing but CD naught by K should be equal to W. So it's very clear from here that CL is fixed because of CD naught by K. You cannot have any other CL. CL is fixed value. As far as V is concerned, it goes on changing with altitude. That is, if you are at some altitude, rho 1, you have different velocity as compared to an altitude rho 2. But you have to ensure that the rho and speed combination should ensure that lift is equal to weight. That is why there will be a particular V given by this equation for a particular altitude where you can maintain cruise and same time thrust required minimum. This is clear? This is very, very important, right? CL by CD max. If we plot CL by CD versus CL, or let's say for alpha, then the figure will go something like this. So there is a typical alpha for which CL by CD is max. This is CL by CD max. What is the message from here? Let us understand one thing from pilot's point of view. Suppose we are telling pilot to fly at CD naught by K and it happens to be 0.2. Let us say. How the pilot will generate that CL? CL, how do I generate CL for an aircraft? We know CL is CL naught plus CL alpha into alpha. That means the pilot has to rotate the airplane to a requisite alpha so that CL is 0.2. Now, if you are telling that you have to fly at CL equal to 0.2, which is basically for thrust required minimum case, then we must sure that this alpha has to be 0.2 for that airplane. Then only you can get CL by CD max, whatever you are requiring for. This value of alpha and CL by CD max combination will go on changing for different aerofoil, different allowance number. So one has to really generate a huge wind tunnel database and create this database to understand what is that alpha at which I get CL by CD max, and then I translate this alpha to CL, and from CL I translate to speed, because finally the pilot will be following the speed. Okay, here the airspeed indicator, he doesn't have any angle of attack indicator. So he doesn't fly with an angle of attack. He will go to the altitude. He knows that at this altitude, if I fly around this speed, which was computed by the CD naught by K condition, so he will maintain that and trim the airplane such a way that there is no change in the altitude. So actually he will be flying at thrust required minimum, right?